Hello everyone. Welcome to this video, this stock video about asymptotically optimal hardness for k-set packing and k-Matroid intersection. This is a joint work with Wong Lee and Ola Svensson. The goal of this talk is to present to you a hardness of k-dimensional matching, which is essentially the question of understanding how difficult finding a matching in a hypergraph where hyperedges have size k. So let's get straight into it. So what is the problem we're going to study? It is that of k-dimensional matching. You're given a k-partite graph where edge contains up to k vertices, and your goal is to find a maximum size subcollection of disjoint edges. So this problem generalizes matching in graphs, in bipartite graphs, when k is equal to 2, and so is solvable in polynomial time. Whereas as soon as k is greater than 3, you end up with a problem that is NP-hard and is in fact listed in Karp's list of 21 NP complete problem. So here on the right, you can see an example of matching in a 4-partite graph where the matchings are the blue edges. So you might be wondering why we care so much about this problem, and in fact, it's because this problem is a subproblem of many important combinatorial problems. For example, k-dimensional matching is a subproblem of k-set packing. It is also a subproblem of k-Matroid intersection, and both k-set packing and k-Matroid intersection are subproblems of k-Matroid parity. I won't describe those problems in the talk, but I just want to say that they're important combinatorial optimization problems that have been studied through the lens of approximation algorithm. K-set packing is essentially k-dimensional matching where your graph is no longer required to be k-partite. And so k-dimensional matching is also a subproblem of k-Matroid intersection because you can think of k-dimensional matching as just the intersection of k-matroids where your matroids are partition matroids. Okay. K-set packing, just to have some more like background literature, k-set packing, as we have like k+1 approximation algorithm for this problem. For k-Matroid parity, we also have like approximation algorithm that gives you an approximation factor of k/2. But the best hardness of approximation for all those problems is a result from 2006 from Azan, Safra, and Schwartz, who proved that k-dimensional matching is a NP-hard problem, and that you cannot approximate it within a factor better than k over log k. So here's roughly like the picture. For all those problems, we have order of k approximation algorithm. In fact, there's a long, I mean, most of current research is happy with, getting improved approximation algorithm where we improve k by some constant. Say we get from, sorry, not from k from a constant, but we improve the leading constant in front of k, meaning that Greedy gives you a k approximation for all those problems, and then there's been like local search algorithm would give you an improved approximation of like k/2, sometimes k/3. And so all of these research is on the approximation side is trying to beat the trivial greedy algorithm by some leading constant. But it's before our work, it was sort of unclear whether we could not get some algorithm that was much better in the sense that maybe we could hope for an algorithm that was of the form k over log k. And in this work, I'll just say, sorry. I'll just say that when you can also think about, uh, sorry, I'll just say the following. Once you, if you can also turn the k-dimensional matching problem as a problem of finding a maximum independence set in some special graph called k-claw-free graphs, by just looking at the conflict graph where you contract every hyperedge and you draw as vertices, and you draw an edge between two vertices if the resulting hyperedge intersect, and find a maximum independence set in this graph. Turns out this was proved to be hard to approximate within a factor of order of k, by Lee and Manrangsi very recently. Some of the techniques that we use in this work we use some of the technique that they used in their work. Okay, so what is our main result? Our main result is the following. We prove that k-dimensional matching is hard to approximate within a factor k over 12, unless NP is a subset of BPP. If you want to remember just one thing, it's that the constant might not be so relevant. It is quite small, which is nice, but it's like the message is the following. It is that essentially we can only be greedy by like greed. Sorry, the important message is that um, we cannot beat. There's no approximation algorithm that is better than a constant times k. So as I said before, the previous hardness result was by Hazen-Safran-Schwarz, which is essentially the best hardness result that we had so far, and has been like consistently cited when you're trying to maximize linear submodular function subject to like the constraint that I've shown before. And so this also proves that this is asymptotically optimal, and shows why there was no like drastically better than order of k approximation algorithm. Our result holds for sufficiently large k, which is why it is asymptotic as a function of epsilon. So in the remaining of the talk, I will just explain how we were able to obtain such results. Some of the techniques, I'll go more into details about Hazen-Safran-Schwarz framework, which is something that we use as well in our work. So let's just cite now what are the two main theorems that we prove in this work. The first one is an approximation preserving reduction. So we prove that k-dimensional matching is hard by a reduction from r degree bounded KCSP. So we start by a r degree bounded KCSP with alphabet size r that we transform into a kr dimensional matching instance. And a crucial part is that the optimal matching size in our resulting instance is exactly equal to the fraction of constraints that are satisfied by optimal assignment of our KCSP. So this is the first like technical theorem that we prove. And the second one that we prove is that R degree bounded KCSP with alphabet size R are hard to approximate, which is something that was not necessarily known. It's not the core of their work, but still it is important that we prove this. We prove that R degree bounded KCSP with alphabet size R are hard to distinguish between the following two cases. Either they're like a 1 minus epsilon fraction of the constraint is satisfiable, or only like roughly a 1 over r fraction of the constraint are satisfiable. Here I'm just highlighting this the constant in front of the 1 over r, which is roughly k over k divided by 3, which is important to optimize the leading constant that we obtain in our hardness result for k-dimensional matching. So what does the second theorem tells us? The second theorem tells us that it tells us that R degree bounded six CSPs are hard to approximate within a factor R2. So if we plug this result into our approximation preserving theorem, we prove that oops, six CSP over alphabet size R are hard to gives you a 6R dimension matching instance. So k-dimensional matching must be hard to approximate within a factor k over 12. So it gives you like a very simple, so once you have those two theorems, it's very simple to obtain the following result. And no, I mean, the k over 12 just comes from the fact that we obtain a 6 times r dimension matching instance. Okay, now I'll just go more into more details about how does this entire reduction works. And I'll just start with a definition of constraint satisfaction problem. You can skip this or pause this if I'm too slow or too fast. But essentially, a KCSP is just almost a hypergraph, except that you have, you should think of your vertices as variables that you assign some label from R1 to R. And each hyperedge is in fact a constraint, and so to satisfy a constraint, there's a set of assignments in R to the k. For example, you can think of this as sets of linear equation mod, sets of linear equation containing k variables mod R. This gives you like a k-CSP instance. And for us, what will be important is the degree of the CSP. This is, so we say it's d degree bounded if every variable appears in the d constraint. And I'll just wrote down that an assignment is a tuple of like, so it should be contained, it's a tuple, a label for every variable. And what you showed on the previous slide, the value is the fraction of constraint that is satisfied by an assignment. But yeah, you should think of your favorite hard problem, maybe some sets of linear equation, or maybe some SAT problem. Anyway, okay, let's just recall that is the main theorem. That k-dimensional matching is hard to approximate with a factor k over 12. And what is our approach? Our approach is the following. As I said, we want to encode satisfying assignment of CSPs as matchings. And so how are we going to do this? Well, the hope is that we will each each edge in our resulting hypergraph should correspond to a constraint in our CSP and a satisfying assignment of that CSP. I'll be more careful in later, but yeah, really you should think of, you start from a CSP, you look at a constraint, and you look at a satisfying assignment of that constraint. This constraint and this assignment should be encoded as an edge in your result, as an hyperedge in your resulting instance. So what do you want to preserve? Well, you want to preserve consistency. So meaning that let's look at two constraints in your CSP where some variable occurs in both constraints. You want to make sure that your satisfying assignments are consistent. So if in one constraint you've assigned, let's say, x1 to 0, and in the second constraint you've assigned x1 to 1, those constraints should correspond to edges that intersect in your resulting instance, because you would like to say that, because you remember that the problem that you're studying is the finding a maximum matching, so any matching should be corresponding to a satisfying assignment of your CSP. Just the same thing. So yeah, so the hope is really that like satisfying assignments that are inconsistent should correspond to to edges that intersect in your k-dimension matching instance. And so the parameters that dictate our construction should be one, the number of constraints that you have, meaning that because you have more constraints, you will have more intersection in your resulting k-dimensional instance, and also the alphabet size. So those are the two parameters that define this construction. You'll see some pictures later that will help you if this isn't clear. And this approach is the one that was used by Asymptotically French Fart. So in that sense, we're not a genius. We're just looking at their approach and adapt it. So what is their approach? Asymptotically French Farts start from a deregular KCSP over alphabet size and transform it into a k-dimensional matching. The exact CSP that they start with is a 3 linear sets of linear equation mod R, each constraint containing 3 variables. But it's an arbitrary deregular, so the degree D is bounded, is arbitrary. And what they can obtain is that they obtain a k-dimensional matching instance where the arity, so the number of vertices of each hyperedge, is R log R, sorry, which gives them a k-dimensional matching instance, hard to approximate within a factor of k log k. And in their paper, they also prove that the result is optimal. They use disperser graphs and show that under the assumption that, I mean, don't phrase it exactly in this way, but when D, the degree is like arbitrarily larger than R, you will incur some, like your edges will like grow as a factor of the form R log R. Should also say that their reduction is not approximation preserving in that they encode satisfying assign. They prove this reduction, but it doesn't go both ways in the sense that a matching in the resulting instance doesn't transform automatically in an assignment of the variables in their CSP, and they have to work a bit harder there as well. Okay. What is our main technical contribution? Well, it is the following. First, we prove that their hardness holds only if the degree in their CSP is very large compared to the alphabet size. In particular, if D is equal to R, we can obtain a very simple construction, which allows us to prove the theorem that I've given you before, this approximation preserving reduction, which we can construct in polynomial time, depending on the number of variables, constraint, and alphabet size. So it just remains to prove that R degree bounded CSPs are with alphabet size R are hard to approximate because all known hardness result for KCSPs have potentially a large degree. So this is the theorem, sorry. And the way we obtain this is using known method for sparsifying CSPs, in that we start from an arbitrary deregular KCSP and sparsify it by dropping some of the constraints with a certain probability and prove that the resulting CSP is hard. So this has been used in proving, as I said, that maximum independent set in k+1 claw-free graph are hard, in connectivity problems and optimization on bounded degree instances. So the proof strategy is to start with a deregular KCSP with alphabet size R that is hard. So this is a known result by Xu-Yun Chan. And now, once you have this hard CSP, you can drop every constraint with probability R over D. This, in expectation, gives you a R degree bounded KCSP. Maybe you need to do a few deletions, but that's okay to handle. And then we obtain an R degree KCSP, R degree bounded KCSP, well, over the same alphabet. It's, what we lose by doing this is the following. We lose quite a bit in the soundness. So we cannot maintain the same soundness as before, but we can still prove that the soundness is of the form 1 over, like 1 over R. Yes. And so again, this is the same thing. So once you have the following theorem, you can prove that 6-degree bounded CSPs are hard to approximate within the factor R over 2. And with the approximation preserving reduction, you directly get that k-dimensional matching are hard to approximate within the factor k over 12. So this is it for the main outline of our results. In the remaining time that I have, I'll just explain the reduction a bit more precisely, and hopefully all of this will make more sense. I'll also detail this sparsification. All right. Let's explain the reduction and the gadget construction, and then talk about the sparsification really quickly. So remember that we're starting from a R degree bounded KCSP over alphabet size R, and we want to reduce the problem of finding satisfying assignment of those CSPs to the problem of finding a maximum matching in some k-dimensional hypergraph that we're going to construct just now. We will work with the following example that hopefully convinces you that will hopefully convince you that we can extend it to those structured CSP that I've talked about. So here I'm going to work with the following 3-in-3 problem, which is a set of equation mod3, each depending on 3 variables, where each variable can take value either 0, 1, or 2. I'm just going to start with the instance pi as follow. You have 3 constraints, and each variable appears in at most 3 constraint. Here x1 appears in at most 3 constraint, k is equal to 3. What is the goal? Again, we're going to construct a k-dimensional matching instance. Each hyperedge that we're going to construct should correspond to a constraint in our CSP pi and a satisfying assignment of that constraint. What does it mean? It means that if I look at C1, who has as a satisfying assignment 0, 0, 0, then there should be an edge in my hypergraph matching instance corresponding to C1 with that assignment 0, 0, 0. Remember that the hope that we had is that 2 edges intersect if the corresponding constraint and their satisfying assignment are inconsistent. What does that mean? It means that if I look at the constraint C1 with assignment 0, 0, 0, and the constraint C2 with 1, 0, and 0, both of which are valid for C1 and C2 respectively, then the edges corresponding to those constraints, those assignments should intersect in my high dimensional matching instance. Why? It is because in the first constraint I've assigned 0, 0, 0. In particular, I've assigned x1 to 0, while in the second constraint I've assigned x1 to 1, which is locally satisfiable, but not globally. Okay. So how are we going to do this? We'll start by constructing a variable gadget, and then we'll combine the variable gadget together. So what is this variable gadget? So fix a variable and fix an assignment or label to that variable. So fix, for example, x1, and let's say I is x is 0. For a variable and an assignment of that variable, we'll partition an R by R grid into R disjoint subsets of size R. What do the set correspond? Each set the jth set will correspond to the jth constraint in which variable x occur. More precisely, we'll look at the following picture. We will have, say, r squared sets indexed by I and j, where I is the assignment and j is the jth constraint in which x appears. For example, here the red set corresponds to the variable x1 set to 1 and the first constraint. The second red set corresponds to x1 set to 0 and the second constraint in which x1 appears. If I look at the blue set now, this corresponds to x1 set to 1 and the first constraint in which x1 appears. This set here corresponds to x1 set to 1 and the second constraint in which x1 appears. So you can see the pattern that appears. And the final variable gadget is this one highlighted here. That is just the combination of those r squared sets. What is important here? Each color corresponds to an assignment of a label to a variable. In particular, note that edges of different color intersect, meaning that x1 should not be, if I take a matching in this variable gadget, then a matching will be monochromatic, meaning that meaning that I can assign so in a matching in my variable gadget, I can assign a label to my variable. And this is very important. This construction crucially relies on the fact that I have as many constraints I have I have as many constraints as I have assignments, um, which is what was problematic for Hazen and Schwarz construction. Okay, so once I have a variable gadget, what do I do? Well, I will combine the variable gadget as follows. So let's look at this constraint and let's assume that C1 is the first constraint in which x1, x2, and x3 appear. So I construct a variable gadget for x1, for x2, for x3. Same gadget. How do I assign, so far, those gadgets don't encode the constraint C1. How do I encode the constraint C1? Well, what is a satisfying assignment of C1? A potential satisfying assignment of C1 is, for example, the assignment 0, 0, 0. How do I encode this? I will look within the variable gadget of corresponding to x1. I will look at the index of the constraint as well as the label that has been assigned to x1. So here, it means that I've looked at the set as 0, 1, corresponding to S1 set to 0 and 1 being the index of the constraint C1. And I'll do this for x2 and for x3. And then I construct this hyperedge of size 9 in that case, encoding this constraint. Perhaps this wasn't clear, so let's repeat with the second constraint. Another satisfying assignment is, for example, 2, 0, and 1. What does that mean? It means that, so how do I encode this constraint? I look at, within the variable gadget, I look at the set corresponding to x1 set to 2 and the index of the constraint C1. So here I look at S21, where x1 is set to 2 and 1 being the index of the 1 being the first constraint in which x1 appears. They do the same for x2 and for x3. So I find, many, so for every possible assignment of constraint C1, I create an hyperedge as follows. And you can clearly check that, um, I mean, those edges will intersect, meaning that we'll find one assignment for constraint C1. And I do this for C2, for C3, and so on, all those constraints. Another, like, here you can post a video and check that you can, for example, for this assignment of 1, 2, and 0, you should create this hyperedge. Okay, so this concludes the reduction. And you can formally prove that any matching in the k-dimensional matching instance constructed here corresponds to a global assignment of your CSP, and that the number of constraints that are satisfied um, by this assignment is equal to the matching size. And that for any, so you have like a one-to-one correspondence, any satisfying assignment to your CSP can be translated into a matching and vice versa. And that the number of constraints for that assignment is equal to the matching size that you will find, which is why you have an approximation preserving reduction. Okay, let's continue briefly and talk about the second point. This reduction takes polynomial time in the number available constraint in R to the k. So let's talk briefly about the hardness of approximating R degree bounded KCSPs with alphabet size R. I'll be very brief. But essentially, we want to prove that R degree bounded KCSPs with alphabet size R are hard, meaning that no polynomial time algorithm can distinguish between whether almost all constraints, whether there's an assignment that satisfies almost all constraints, or whether there's an assignment that satisfies only roughly 1 over R of them. How do we prove this? Well, we start with Xu-Yuan-Chan theorem, which tells us that unless P is equal to NP, um, something stronger holds if we assume that our CSP is D regular. So D here should be thought of something that is much greater than R. In that case, we even have that it's hard to distinguish between whether um, there is an assignment that satisfies almost all constraint or at most 1 over R to the k minus 2 of them. Okay, so what we will do, starting from this, we will sample like a subinstance by dropping each constraint with probability R over D and prove that the remaining instance is hard. Note that by doing so, we cannot ensure that what we cannot prove is that the soundness is maintained. So our soundness will drop, but this will still be sufficient for our result to hold. So by sampling, sometimes we could obtain something where degree is not exactly R, but by doing like some extra like deletion step, we can ensure that we end up with a R degree bounded KCSP. So we can show that the degree of each variable is like, we can sort of assume for now that when we sample the subgraph, everything has degree at most R. Okay. Let's say pi prime is the sampled subgraph, the sample KCSP instance, and pi is the original um, CSP instance that we obtained by applying Xu-Yuan-Chan. Completeness is really easy to show in that the optimal assignment for pi will with high probability be a good assignment for the sampled subgraph, the sampled subinstance, sorry. So this is really easy to show. The main like barrier is to prove the soundness. And so we want to prove that there is no satisfying assignment that satisfies more than 1 over R constraint, roughly order of 1 over R constraint. And so how we will do this, we'll fix an assignment and compute the probability that this assignment satisfies more than S prime times M, more than S prime times M constraint. And that we can prove that the probability is something that is at most like 1 over R to the n, something even slightly smaller than R to the n. And why is this good? Well, it is good because now we can just use like a simple union bound over all R to the n assignment and get that with high probability, there is no assignment that satisfies more than 1 over, uh, sorry, yeah, S prime times n constraint. And that's it. I'll let you read the details in this slide or in the paper, but this is just like simple like union bound and simple like probability computation. Let us recall what is the final theorem that we prove. We prove that k-dimensional matching is hard to approximate within a factor k over 12 unless NP is a subset of PVP. This gives us strong evidence that k-dimensional matching is hard to like that no algorithm, no polynomial algorithm could give us like a something drastically better than a constant times k. Note that Hazen-Safran-Schwarz result is a NP hardness result with whereas we use a randomized reduction, so we can only prove it unless NP is a subset of BPP. But at least this explains why we have no order of k approximation. I mean, no approximation algorithm that are like strongly better than order of k. I'll list here a couple of open questions, namely that it would be interesting to bridge the gap between hardness and approximation for k-dimension matching. That studying this problem in online and streaming setting would also be interesting, where we have very few results, and that most of the technique that we use are relatively old. Sparsification and also the framework of Hazen-Safran-Schwarz was known from a long time. So it made sense to also look at maybe old and all combinatorial optimization problem, NP-hard combinatorial optimization problem, and um, see whether we could improve the hardness result in light of the recent progress that we've obtained for CSPs. With that, I thank you very much, and I look forward to see you at STOC. Bye bye.